Thanks so much for the introduction, and thank you for the invitation to be able to speak. Huge thank you to Midas for sponsoring this and putting. I think it's very important that we have like-minded people from diverse backgrounds being able to talk about this. And then again, my biggest thank you undoubtedly to my lab and my students. The only reason I'm standing here is because they submitted something for us in our group. So this is really just, a presentation of their work. So I'm a neurosurgeon here at the University of Michigan, and I also run the machine learning for neurosurgery lab. And this talk is really about, our path towards bringing artificial intelligence into the operating room. I think it's a really important application. It's something where we need a lot of innovation. Surgery is very slow. I think our innovation is often outpaced by other industries, probably for good reason. Patient safety is very important. However, we still need to improve the way we take care of surgical patients, no doubt about it. I'm obviously partial to brain tumor patients because that's what I spend most of my time doing, and that's what this talk is going to be focused on. Really, how do we intelligently image the brain itself, but also the tumors that affect it? So this may be news to some of you, but that's a brain. So this is what I spend a lot of my day looking at. And the thing that we're really trying to do is care for this. We're trying to care for the brain. And we do know that unfortunately the brain does get tumors. And we have two things in mind when we're thinking about how best to treat these patients, right? We can't amputate the head. That's not an option. Unlike some of my other people, they can, if you have cancer in an arm, for example, they do amputate arms in order to be able to save their life. However, amputating brains is not an option. So we have to think about the brain. And then also we have to think about how do we safely remove that tumor, right? So that's really been the task at hand really since the turn of the 20th century. So Harvey Cushing was the main innovator of neurosurgery, and he really defined the principles as to how we treat these problems. And this is about as far as we've gotten. We need to protect the brain, and we need to take the tumor out. Really, that's as far as we've gotten. We do have some chemotherapies and radiation treatments, but the problem is we're still really stuck in this paradigm of basically saying we got to take out what we can safely see without removing too much of the normal healthy brain and potentially giving the patient a neurologic deficit. So this is where we've been. This is why I really think innovation is important and why we need university settings, university hospitals, investigators, neurosurgeons, research scientists to be able to move the needle on this problem. And the reason why brain tumor surgery is hard, right, is because as a surgeon, I'm going to do an incision, I'm going to remove a portion of the skull, and then this is ultimately what you see. And, this looks like normal brain. This is just a normal, if you were to open my head, that's exactly what you would see. And you think, I'm supposed to remove something here. I'm supposed to know what I'm supposed to resect. I don't know about you, but I don't feel like I have any healthy brain to give up, to remove, right? Just remove the tumor, don't remove the healthy brain. But the problem is that this all looks very normal, and that's how it is for the majority of brain cancers. And the reason is because the tumor doesn't grow like a golf ball. I think of it even when I was a medical student and I was thinking about surgical oncology, is that there's basically a ball, it lives in there. Just get around the edges and just remove the ball, right? Unfortunately, really no cancers grow like that. They grow into the normal tissue. So then you're faced as the surgeon to say basically, well, how do I find the area that's infiltrated with tumor? And that's still a very open question. The United States government just released, as part of their ARPA-H initiative under Joe Biden, basically trying to give out $1 billion to solve this problem to investigators. They identified a certain set of touch points, areas where we think a lot of innovation is going to really improve patient care, and brain surgery was one of them. So again, this is very much an active problem. And, this is about pathways and journeys and those sorts of things. So that's me on the right with the goofy yellow cap. This was when I was a neurosurgery resident. So we've been doing this now for really over a decade. And as part of these surgeries, what we were trying to do is to develop an imaging technology to be able to differentiate between normal brain and cancer. That was really the goal. And these are some of the pictures. This is the microscope that we developed here at the University of Michigan. This really was a brainchild of my mentor, Dan Oringer, who's on the left in the photograph. And, we have this nice looking imager that takes excellent high resolution optical images in real time in the operating room. That's great, right? But an image is not a decision. It's not a decision to remove or leave, right? You need to move forward and say, okay, now that I have this image, I need to make a definitive clinical decision of whether I should continue with this resection. And that's really what we were trying to work towards is, can we use computer vision, AI, to be able to make this decision for us? Because this is a really hard problem. And again, like I mentioned before, is this brain or is this tumor, right? We need to know on either side. Don't remove any normal brain, but you got to remove the tumor so that way the patient has a longer life. So that was exactly what we did. So I like to say this is before AI was cool. So just to give you guys a sense of this, we really started this research in 2016. TensorFlow, which was the main tensor library used to train deep neural networks, didn't come out until about 2015 or so. So again, this was right at the beginning of that. And we were able to show that yes, if we bring AI to the operating room, we're actually able to make these AI diagnoses. Luckily, this is at a time, again, when AI hadn't really infiltrated into healthcare. We didn't see a lot of innovation in that direction. And luckily, the New York Times picked this up. Credit to them for recognizing that this is going to be a big deal. So this is really the work from my lab and from my student Akil Kundaputi, where we developed this technology called fast glioma. All AIs need a fancy name now, so we named it fast glioma. So the idea is that when we're removing these tumors, we're able to image the surgical margin, and we're able to have a prediction. So if I image a specific region, what proportion of that region is tumor and what proportion is normal brain? And we were able to give, train an encoder. So this was a big model. Think of this as GPT. Yes, good. You can think of this as GPT. And then we used this very large model to be able to train a slide scorer model that's basically like ChatGPT. In this case, rather than being trained for chatbot or being trained for conversation, it's being trained to be able to determine how much tumor is in this specific specimen. And we were able to release this across the globe. That was one of the things I was most proud about, is that if you have collaborators and you're part of a university setting, these are people who are your community as neurosurgeons, right? There's not that many of us, so you can call your friend on the phone and be like, we have this idea that we would like to roll out. So we released it at UCSF, NYU, and Vienna, and we were able to show that the predictions are consistent and accurate across the world. So this was a really big step forward, something that I'm especially proud of as an assistant professor. So these are really the results that I think are most important to know, is that we currently have a set of standard of care options for patients. One of those is intraoperative MRI, and one is fluorescence-guided surgery. Both are trying to do the same thing. They're both trying to identify tumor in the resection cavity. And this is an ROC curve over here, and the big purple star over here is our performance. And then this is the current standard of care that a patient would get at a university hospital like ours if they weren't using this technology. So we were able to show definitively that this really outperforms what patients are currently getting when they're diagnosed with brain cancer and then ultimately undergo a surgery. And we were able to show, most importantly, that the likelihood of these patients receiving the optimal surgery, the best surgery we can do, goes way up. And the misses, the errors that we make as surgeons, goes way down. And that was a really important moment for us in demonstrating this. So I want to stick to time, so this is my lab. I couldn't be prouder of this group. I think there's a lot of momentum behind this. I think this is just one of the many AI journeys that we have here at Michigan. And again, I think that to the students in the room, AI is not solved. OpenAI, Google, these people are running out of ideas. More language, right? More language modeling, right? They've run out of internet. There isn't any more internet. We need brilliant young minds at universities to work on these problems. So I encourage people to continue to move forward. We need new ideas, right? Not more GPUs. We need new ideas. All right, thanks very much.
Hey Todd, what's next? I mean,
Yeah.
Let's look into the future a few years.
Yes, absolutely. So I think there's really two main directions that we're heading in. We're working a lot more in non-invasive imaging. So, these are basically MRIs and CTs. We're trying to better understand what are some of the prognosticators for how successful we're likely to be with surgery, but also how is that patient likely to do. And then also, we're really trying to improve the amount of information that surgeons have in the operating room. We're getting an estimate as to how much tumor is infiltrated at this margin and how well we're doing with the surgery, but ultimately what we want to know is at the time of surgery, how much improvement, overall clinical improvement, have we bought that patient as part of that operation. That's a predictive task, like sort of a forecasting task, which is generally harder, but right now we're accumulating data to be able to answer that. Oh. I can hear you.
Okay. My question, so I'm a sociologist, so I'm really interested in how people interact with these sorts of tools that get created. And I guess I'm curious with the graph that you showed of like the true positive versus false positive rate and how your tool is performing very well on those metrics. Because I'm wondering, is that showing how surgeons are actually, like the results of, the real world results of surgeons actually using these tools? Or is that, or that's just the kind of, the, before the surgeon interacts with it? I guess I'm curious, like, are there ways that, are you looking at how surgeons are actually like responding to these recommendations that these tools are making, and like whether that affect, whether surgeons' interactions with these tools or responses to these suggested decisions, like how that, how that looks?
Right. Yeah. So it's an important question because you can imagine that by just using the tool, it's going to change the way you behave, right? And in this case, because this is not an FDA-approved device yet, it was non-interventional, so we couldn't allow the surgeons to actually resect more as a function of these of the results here. However, I do think that it is important to note that as we start to use these models more, AI in general, it will change behavior, right? It will certainly have an effect. I know it'll have the effect the way that I think about surgery and how successful we're likely to be with these. But I think that, it's kind of both a positive and a negative, right? We certainly don't want it to affect it in a negative direction, but I also think that we need to do better. So we need something to divert the way we behave, in this case with surgical resections.
Hi. Do you have advice for computer science students who want to get involved in AI in scientific fields where they don't have expertise?
Yes.
For example, you mentioned like Google, OpenAI. It feels like they are only doing LLMs, and if
Right.
they want to do like biomedicine,
Yes.
do that without that.
Right, absolutely, yes. So this is where universities play the central role of the future of AI, right? If you look at Google or OpenAI, especially OpenAI, they just went all in on language. Like we're forgetting more or less about everything else. They stopped Sora. Like, what do they do? So this is where I think students are so important to realize that I think the next generation of development in AI is to be more in applied fields, and we're going to need more interdisciplinary students. Where does that happen? That's like the definition of a university, right? So I think that the ability, so for example, I take students from DCMB, I take students from computer science and engineering. So I'm directly supervising students from computer science and engineering with the explicit task of trying to train individuals that will be able to do this cross-disciplinary research. So please reach out to people outside of your specific school or college or whatever it may be, because I promise you there are going to be talented people who want to work with you. So, yep.
We have time for one more quick question.
Small question. So one, in terms of the use of the tool on patients, is it does it range from children to adults, or is there one, segment that it's focused on? And then secondly, there was a study, and I think it was featured in the November conference, MIDAS conference, that talked about how radiologists, their outcomes and diagnoses or detections was increased with AI. But then when they were measured alone without AI, their skill set actually degraded. So what are your thoughts about that piece on your physicians or diagnosticians?
Yes. So the model that we trained was supposed to apply to both children and adults, and also across many different tumor types. We were able to show that while we trained it kind of specifically for these diffuse gliomas, they actually generalize across a lot of different brain tumor types, including children. And then to your second point, yes, there's been some really good papers, mostly published in the clinical literature like Lancet and JAMA, to look at how do a diagnostic performance change when physicians are working with LLMs. And the effects are a little bit counterintuitive in the sense that if you look in a primary care setting, often LLMs do extremely well because it's very question and answer based, and you see very good performance for diagnosis like things like strep throat, for example. When LLMs work with humans, the performance goes down on both sides. LLMs do worse relative to their performance alone. Humans do worse to their performance alone. I think what's happening in those settings is these models are meant to be very affable and very nice to us. So when we ask a bad question, it's like, that was actually a really good point that you made. When in reality, it wasn't a good point. You are wrong, physician. That was not a good point. Sorry, I was right. So I think there's a way that it can actually divert bad thinking in a worse direction, right? And it doesn't have a good stopgap because it's trained with reinforcement learning to be very affable. It doesn't have a good way to say, you're wrong, that was a bad point, this was the right answer. So that's one sort of armchair psychological explanation about what I think is happening. Thanks.
Super.
Well, let's put our hands together.
All right. Yeah, thank you so much for the introduction. I'm in the Department of Radiology, but I'm a computer scientist, and I also have to admit that I slightly changed the title of the talk now to put more focus here on the neuroimage analysis aspect. And I also need to acknowledge that most of the work that I'm presenting here today was done at the University of Calgary in Canada. I was a faculty prior to joining Michigan last summer. All right. So what's the goal of this talk? I want to talk a little bit about how to build a classification model in neuroimaging here with respect to or with a focus on Parkinson's disease classification. And the goal is basically to utilize a T1 weighted MRI image. Here it's only a 2D axial slice, but a 3D image, and then to build a classifier that classifies an image into Parkinson's, yes or no. So binary classification problem. And we were approached by clinicians who wanted to know more about that and to potentially put it into clinical practice, but more so also to learn more about if we can find additional biomarkers here. I will talk a little bit about how we overcame here challenges with respect to data scarcity, which is a big problem here, and also show then the need for trustworthy AI approaches that go beyond classical saliency maps that you might know, where you can then see like the important or unimportant locations the classifier utilized, but also how we need to utilize approaches here to identify shortcuts and resulting biases in those models. And then we will see like how we can improve upon that by using targeted data harmonization, and also how synthetic data can help you to learn more about the models and how and where those biases actually manifest. Okay, as I said before, the task here, the clinical task is pretty easy. Parkinson's disease classification. Parkinson's is the second most common neurodegenerative disease, affects more than 10 million people globally. And unfortunately, there is no cure available, but early diagnosis helps to manage the symptoms. It's usually being diagnosed by neurologists, which then look into like if there is a slowness in movements and at least one additional other cardinal motor syndrome like a tremor, but you can also have like a combination of motor and non-motor symptoms. And basically the task that we were asked to do here by our clinicians is can we build such a classifier, as I said before. How did we approach that? Super simple, like for everyone who's working in computer science or AI, what we did here was to just use a standard convolutional neural network here that we were utilizing before for other classification tasks in Alzheimer's or brain age prediction, where just the 3D MRI goes into the model being processed through different layers here, and then the output is just a binary classification problem, either Parkinson's, yes or no. The major problem here is, it's a supervised classification problem. The major problem here is data scarcity. For example, in Calgary back then, labeled MRI data from Parkinson's patient, we only had 72 cases available, a similar amount of healthy patients. And the problem there is that in Canada, usually you can't just pull additional data from the radiology packs, because you need explicit patient consent for being utilized in research. So we were kind of bound to those cases that we had from a study setting there. And then what we tried to do to improve upon that and to get like additional training data was to pull data from additional centers worldwide, approaching collaborators within Canada, but also outside of Canada. And in the end, we were able to get more than 1,800 T1 weighted scans from healthy subjects, but also Parkinson's individuals from 40 centers worldwide. But this took a lot of time to manage. And as you can see, like, this is not a huge amount of data, which then leads to problems later on. But let's look first at like how this works. You can just train such a classifier. Accuracy is quite okay given the complexity of the problem. I don't want to go too much into detail what the inputs here were, but like raw imaging data, but also then preprocessed data. And in the end, the accuracy here was about like 80%, which is okay in this task, and you can outperform classical feature-driven machine learning approaches. We then also utilize the expertise of our clinicians to confirm that the regions that the model uses here are actually regions that are known to be affected by Parkinson's. So we generated here simple average saliency maps across the whole population that we were using and sharing that those to our clinicians, and they were satisfied by that and said like, okay, this is we trust this this system. But then the problem is that we noticed, you can see it here in the table, we also had an independent test set, which was one side that we left out for testing, not being utilized for training. And you can see, depending on what the actual input is, there is a sudden drop in accuracy. And this kind of concerned us, and we were interested in like finding out what the actual problem is. In the end, we used a large and balanced multi-site data set. So we had a similar amount of patients with Parkinson's and also healthy individuals, also age matched. And explainable AI confirmed like that the regions that the model we're utilizing here are sound, but why did that not generalize better? And the problem is that this multi-site data is a curse and a blessing. So we needed it to actually train such a model. But then the problem is that this is super complex. So you have like 3 different vendors of scanners here, 90 different scanner types. Every institution runs a slightly different protocol on those scanners, and also the combination of 1.5 and 3 Tesla data. And while the overall data set is balanced, the single sites were highly imbalanced with respect to the demographics, but also to the disease status. And in the end, our MRI expert on the team confirmed that different scanners can induce subtle features into the image that as a human you hardly see. And in the end, this leads to shortcut learning. So we have a bias in the data that then the model uses to convert into an algorithmic bias. Simple example from chest X-ray, like if you have set a marker here, it's known that those markers can be utilized for disease classification where there is no causal relationship between the marker and the disease. And similar things are happening here. How can we detect it? We used a super simple approach here. We just utilized our trained model here with an accuracy of 74% on the binary classification problem, froze the feature extraction layers, and then try to classify different confounders or mediators here. So sex, site, and scanner. And you can see that the accuracy for those additional factors here from the same features that are being utilized for Parkinson's disease classification are on par or sometimes even higher with the actual classification task. And we then also computed those saliency maps here for the different scanners, and you can see from top to bottom that each site or each scanner configuration induces slightly different characteristics in the images that the classifier then leverages here. And in the end, those insights based upon this simple classification task led to 2 new sub-projects to improve upon that. First of all, we tried to develop new data harmonization approaches that utilize generative AI to get rid of those biases explicitly in the data. And then also we wanted to learn more about like how and where in the networks those biases actually manifest. And that's why we did with synthetic data with our SIMBA framework. Let me quickly talk about this new data harmonization approach for brain MRI. It's prior knowledge driven. What we do here is we induce an explicit causal graph where we specify those confounders, for example, that lead to the brain image, and then we train a generative model that then can accept a new or an unseen brain MRI. It's being mapped into the latent space of the model where you then can intervene on the site variable and push it back into the image space, which then removes the side effect by the scanner, but leaves all of the other biological effects that you want to keep in there and this is something that we are currently still evaluating, but it looks like that this basically solves the shortcut learning. The other thing I was talking about is the synthetic data that we utilized. Similar approaches exist already in computer vision and machine learning, where you have synthetic data, where you can induce different biases and shortcuts, and then evaluate how your model reacts. But for neuroimaging, something like that doesn't exist, and you cannot really utilize the computer vision 2D data for like this approach, or like for those kind of problems, because the biases are like super different, and you also can't utilize real-world data here because we have a combination of biological and non-biological effects that you often don't know about. So what we did here, it's also a generative AI approach where we have a template image, and then you can induce different disease regions in the image that you want to classify, and then also locate different shortcut options for the model, and you can generate an infinite amount of data here and then test your model and benchmark your model against that. We did this already to benchmark explainability methods if they can pick up those shortcuts, bias mitigation approaches, and we are now developing new targeted approaches on like how to debias the different layers of the network, because it depends on like the layer or like the shortcut where in the network it's actually manifesting, which you can test with the Simba framework, and then utilize it to debias your method. Okay, a quick conclusion here. What initially seemed like a super simple problem, just images in, classification result, got super complicated. Getting data from multiple sites is needed here, but time consuming. And that also leads to interaction between biological and non-biological factors that then lead to a data bias and an algorithmic bias in the end. And we needed multidisciplinary domain expertise here to detect that, clinicians to confirm that it's doing something clinically relevant, and also MRI experts to learn more about those shortcut possibilities here, which then in the end led to additional technical research and to analyze different shortcut learning effects, but also then to how to mitigate that and to generate synthetic data to test models comprehensively. All right, that's the end of my talk. Thank you.
Big button. About 20, 30 years ago, a lot of Parkinson's patients were re-diagnosed to have Lewy body disease. So I'm curious, as right now with your brain imaging, are you able to differentiate between the different kind of neurological conditions?
That's something that we are currently actually trying to investigate. The problem there is the data availability of those different subtypes. But that was one of the major goals initially, not to put it in clinical practice, but to try to find imaging biomarkers of those different subtypes. Yes.
Any other questions? We have time for one more. Okay. Let's put our hands together one more time.
Thank you.
Thank you very much.
Hi, everyone. Thank you for the opportunity to speak here. My name is Benjamin David. I'm a research faculty in the Department of Biomedical Engineering. I'm here on behalf of Paul Jensen and representing the rest of the Jensen lab in our work developing robot scientists that design, execute, and learn from their own experiments. So our group was inspired by the advances in AI systems that play games. And these systems use a technique called reinforcement learning to master board games such as chess, Go, and shogi. These systems consisted of an agent that would design their own experiments. These would typically be moves on a simulated board, and in return, they'd receive a signal that said ultimately whether or not that move helped the agent win, lose, or draw in the game. And with this reward, the agent would update a model that was internal to the agent, and the model's job was to try to predict the outcome of future moves. It would use this model to help plan new experiments and begin a cycle of learning iteratively. Right? Many people have seen reinforcement learning before, but it's a really powerful tool for learning things without any prior knowledge. And that was the amazing thing about these systems, was that they had no knowledge of the games that they were playing when they set out to try to learn how to beat the world's best players at their respective games. We thought it would be really interesting if we could turn some simple biological questions into a game and have one of these agents learn to play biology. So we started working on our system called BacterAI, and BacterAI is allowed to design experiments, and then we would go into the lab and carry them out, and in return we'd send some data back to the agent. It would update an internal model that's trying to predict the outcome of the experiments that we were designing, and then it would use that model and the new information it has gained to design more experiments and continue in cycles of learning. Now, when we've talked about BacterAI in the past, we typically talk a lot about the left side of this loop. We talk about how we design the models, what policies we use to select new experiments. But it turned out that the biggest challenge in designing BacterAI was the right side of this loop. And that was putting together an automated platform for doing all of these experiments and coming up with a way that we could turn BacterAI's experimental requests into data so that we could train the model. The key difference between these AI agents for playing games and BacterAI was how difficult that problem was. In the case of the AI agents in their games, the experiments could be done almost instantaneously. They make a move on the board and they have a perfect simulation of the game. BacterAI doesn't know, though, that when it requests an experiment, it's kicking off an entire process in the lab. It just thinks it's playing a game and that we're taking a very long time to make its moves in between every cycle. So I thought the best way to share some of the engineering work that went into building our automated platform would be to walk through a day in the life of one of BacterAI's experiments. So in the spirit of a show that I really like to watch growing up as a kid, let's see how it's made. So BacterAI's experiments start within the computer where it begins filling out a queue of runs. And the simplest question that BacterAI can answer is, what nutrients does a bacteria need to grow? And so with its experiments, BacterAI is allowed to vary the concentration of different components in the media, the different nutrients that it has available to it. And then our job is to go and create bacterial cultures with those media and measure the growth of the culture over time. So once BacterAI has finished filling up a queue of runs so that we can run a batch, we have to start planning out the logistics of making those cultures. The first step is to lay out all of those experiments onto plates and assign them to wells on these plates. We grow all of our bacteria in standardized plastic dishes that have 96 wells. So when BacterAI comes up with a set of 96 experiments, we start scheduling those runs onto these plates, and we begin filling out the plates. We have a piece of software that helps us do this that randomizes the location of all the experiments, and it also includes some positive and negative controls on the plate that we use for data processing and quality control purposes later on. So once we have these plates designed, it's time to start thinking about how we're going to actually create all of the cultures in the lab. We maintain a fleet of liquid handling robots in the lab and a library of reagents that we use to create all of the cultures. So we developed a piece of software called Porfecto that takes the reagents that we have in the lab and the cultures that we want to make, and its job is to write protocols for all of the instruments in our lab. So it does that in two stages. The first stage solves for all of how we should mix all of the reagents into every well. Every well can have a different amount of each reagent. And then in the second stage, the software actually dispatches all of these operations optimally across all of the robots that we have in the lab. Each robot has a different set of weaknesses and constraints. So we have the software write all of the protocols for us before we run them in the lab. When we actually go into the lab, we start assembling all of the reagents that we need for the day. We store all of our reagents in many different tubes and bottles. So we have one set of robots that takes all of those reagents from the tubes and loads them into a standardized dish that we call a source plate. These are all the reagents that we need just for those days' experiments. In a second stage, we actually begin preparing all the different combinations of media. So we have a set of robots that draw on these source plates, and they begin dispensing varying amounts of every reagent into the wells of the plate. Now, these robots work on a much smaller scale of volume than the previous one, and so they fire tiny discrete shots into the well. I think this instrument is kind of amazing because if you watch it in real time, you can't even see it dispensing into the wells. You have to slow down the video, zoom in, and put a die in there to see all these shots firing into every single well. The third step is we add any reagents that are common to all the experiments, like water and an initial inoculum of the bacteria to get the culture started. So we use an instrument like this that multiplexes all of these operations at once. Pay no attention to the hand in the top right corner in there. I believe the model of that robot is called Undergrad. For certain operations, we still rely on humans to do some small steps because not everything is reliable enough with the robotics to do everything in an automated fashion. This particular operation is so much faster if we use this instrument manned by a human than if we use a robot. once the cultures have gotten started, the clock is ticking, we need to start measuring the growth. So we have a set of robotic arms that moves the cultures from their incubators into plate readers to measure the growth over 24 hours. We take repeated measurements so we can get growth profiles. When we started running all these experiments back in 2020, we could do up to 300 experiments a day. As we got more efficient with our processes and began developing new capabilities with our automation equipment, we were able to do up to 10,000 experiments a day after about a year. Most recently, we've begun to expand our equipment further. So this spring, we're going to be commissioning our newest robot. Instead of having the robot shuttle plates between the incubators and the plate readers, we enclosed everything inside one giant incubator. And so this chamber is environmentally controlled. The temperature in the atmosphere can be controlled, and we can grow a much wider variety of bacteria than we could otherwise. So this whole process, from scheduling to liquid handling to incubation and monitoring, results in growth profiles that we use to send back to the agent, and it tries to make sense of all the results. Now, since we started, we've done over 1 million experiments with the system, and they've been primarily focused on the oral microbiome. For our next 1 million experiments, we're going to be surveying a slice of the tree of life that is much wider. So we're partnering with the Align Foundation to build the world's largest open data set for microbial phenotyping. Our plan is to culture 1,000 microbes in 1,000 different conditions each. Our hope is that we can use this data to build models of growth that will combine a microbe's genome with its environment in order to predict whether or not it'll grow. We hope that this data will help us predict growth in microbes that are understudied and have very little prior knowledge in the literature available. Microbiology is a much more data-limited field than many other fields that we've been talking about today. So with that, I'd like to thank the rest of our lab here. Like I said, this has been a prolonged effort from our lab, and nearly every member of our lab has been involved in either building or expanding this system. And in particular, I'd like to highlight the efforts of the lab alumni who have worked on this project. They were the ones who really got it off the ground and running initially. So if you're interested and you want to learn more about the modeling and everything else, I've included the references to our relevant papers in there. But with that, if there's any questions, I'd be happy to answer. Sure.
So this is a very specific application, but obviously this could be scaled to different things. You have ideas of where else this technology could be used?
Yeah, so the plate readers that we have aren't only capable of measuring growth. So one of the things that we're really interested in is if we can develop assays to measure gene expression and these other things, expand the type of data that we're able to collect the system. I think we can. And one of the benefits and the things that we've done with our engineering is tried to make this system as modular as possible. So every time there's an update to new model architectures that come out or new automation equipment that we can bring in, our goal has been able to be as flexible as possible with having the system run effectively in all those different circumstances. So yes, we're looking at many different types of ways that we can expand.
Okay, any more questions? Okay, great. We're going to move on to our final speaker. Thank you. One more time for Ben. Thank you.
Thank you, everyone. I'm Ali Namvar. I'm currently research fellow in Galban Lab. And in the next 2 days, I will start my job as a research assistant scientist. Today, I want to share the story behind the Stream. Stream is an explainable AI framework for real-time ICU monitoring. I will focus on how we identify the problem, how we choose to use AI, how we build the framework, and what we learn from the process. When I joined the Galban lab, I found myself as a molecular biologist in the full room of the engineer, so it's very tough for me. Yeah, it's really tough. But my background is bioinformatics and working with the big data. So as biologists, we train to think in a system. And in biology, you do not study one gene and claim you understand the whole system. And that mindset helped me a lot when I designed that system. So, but the main question? In the ICU, we have a high data environment. Data coming non-stop from everywhere, from the bedside monitor, lab data, doctor notes, from everywhere, non-stop. The question was simple. When a patient has a dozen of measurements changing over time, how to see the whole picture? Existing score compresses the patient info into one value, and real-time alert system keep firing without giving you the overall direction, like beep, 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 but without giving you the overall direction. So we want to build a system that look at the whole feature all together, respect the relationship between the feature, and give you the best prediction. Oh, sorry. And give you the best prediction you can. We follow the question, not the tools. So the problem required a method that could look at the many features together, respect their relationship, and track how the overall population changed over the time. Optimal transport was a natural fit. It does not change, it does not compare average. It's measure how the minimum work need to reshape one population into the another population. That's why we choose the optimal transport. It's the overall workflow stream. On the left, you can see the raw data, like lab measurement, vital sign, neurological. Those data move into the stream core engine, and it does two things. The first is state detection using optimal transport, and then state assignment using a ruler called Mahalanobis distance. It's not the normal ruler. It's measure how patient close is to the state, and also how well fit that patient to that state. On the right, you can see the clinical output that stream measure, like risk alert, prediction, and explainability. At this point, it's become obvious that it's not a one person or one discipline project. We need a clinical judgment to select the feature, very important, engineer thinking to make a pipeline stable and scalable, and also biology mindset to think a patient as a system. We use two public data sets, EICU and MIMIC. EICU have a near 158,000 patients, and MIMIC have a like 19,000 patients. Near 80 to 19% of effort was data processing, like dealing with data sparsity, inconsistency across the hospital, and data missingless, especially in high dimensional space. And on top of that, we have an optimal transport that is computationally expensive. So it's the most challenging part of this project. So data move into the core stream. But how optimal transport detect the movement, detect the state change? It's asked how much work it takes to reshape one population to another. If that distance is large enough between two distributions, it's it suggests that population has moved into the new state. We use tree optimal transport like a tree judge. Each of them look at the data at tree view, and we assign a new state, and we call new state when at least two of the three optimal transport agreed. So we ran a stream on EICU cohort over 10 days, and algorithm identify 5 states, and each of them have a different mortality and different physiological feature. The key point is the stream is unsupervised. So we didn't define those state before feeding the data into the stream. They are directly emerged from the data. So, but how do we track the patient movement over the time? On the left, at each time point, we track the patient measurement and measure each patient distance from five states. Closest state win the statement, win the assignment. For example, in this picture, state 2 win the assignment. On the right, by connecting those assignments, we get the trajectory. And the key point is, a stream at each time point report why the patient is moving. And even when a patient is stable, some feature can change. You can think of it moving in the same region. For example, moving from here to here. So some feature can still change, and a stream will report that. Another key discovery is outlier signal. We found that some patients get assigned to a state, but they do not really fit that assigned state. We call them a state outlier. Spending more time as a state outlier in the ICU is associated with the higher risk of mortality. Patients who spend a lot of time as an outlier had about 9 times higher risk of mortality than patients who consistently fit their assigned state. The next thing we did was the external validation. Does a stream work somewhere else? We frozen the EICU model and then apply it to the mimic dataset. The question was, does this region show up the same mortality rate here? Does the outlier effect show up again? And we saw that outlier effect showed the 7 times mortality in the mimic dataset, and the mortality rate also is the same as the EICU dataset. We also ran the mortality prediction per hour, and in the 8th hour we reached 0.86 for the EICU and 0.79 for the mimic. It shows us like 7% drop. So based on that, this gave us the external validation of the model. But what we learned from that? First, states were clinically meaningful when we check with our clinician. The second is the explainability is important. A stream did not just report the why patient is moving. It's also report when a patient is stable and why is stable. For example, you get the patient a drug, you see the patient is stable, is not changing, so you want to see why that patient is stable, why the situation is not changing. You can see the report and find out. Also, the external validation show that the model the external validation support that the model can use in the completely different data set. So the last thing I can say is data quality is everything. If you skip the pre-processing, no model is saving you. Try to build a diverse team, like with diverse expert, diverse domain expert, and someone who keep asking what does it mean for the patient. And also try to focus on the problem solving skills, not the tools. Tools will change. They are also now changing with the AI. But the ability to ask the right question is the thing will always matter. Thank you. Yeah, we currently working with the asthma data set. It's have like a 20 million people. We are currently working on that, and we use the new method called quantile mapping, and we are working with that. Yeah, thank you.
Any other questions? Okay, great.
Thank you
Very much.
Yeah.